saying that about chess back in the day. So, I mean, once you've reached the number of atoms in the universe, we'll put aside the question of how do they know how many atoms there are in the universe. But once you've reached it, then if you are 10 to the 80 more times than that, who cares, right? The point is, it's a massively challenging problem, but it's not obvious to me that it's qualitatively different than chess. More important point, does AlphaGo show us the way to do AI more broadly? So, and I would say that it's at least quite problematic. Board games are black and white, they have discrete moves, right? You have an evaluation function, win or lose. Labeled data is essentially infinite, right? AlphaGo started with 30 million board positions. Nice to see you. And then had the ability to label more positions using self-play, right? So when you have essentially infinite labeled data, then sure, that's a great thing. But sure, deep learning is phenomenal, but what if you don't have all these constraints? What if you don't have moves? What if things aren't black and white and discrete? What if you don't have an objective function? And what if labeled data is very limited? Sorry, I keep gesturing like this because I see people coming in and there's still seats. Please don't hesitate to come in. There are seats. There are seats. This is not like a concert. It's okay. You can enjoy it. All right. Here's another key point that I think all of you are very intimately familiar with. Machine learning, right, like many things in our field, is a misnomer, right? Really, machine learning is 99% human work. It's 99% your work, right? You define the target concept. You define the algorithm. If it's a neural network, you define the network design, various aspects of the loss function, and you figure out how to get labeled data, right? All these things are done outside of what's considered the learning system, by people like this. And so when I look at the DeepMind achievement, and by the way, again, I'm not taking away anything from it's a phenomenal achievement. What I see is that the DeepMind human team, right, over 100 researchers and engineers, they defeated Lee Sedol, right? They had a little help from a machine. So anyway, let me not belabor this point, but in terms of AI, what I really like the statement, superhuman performance on a narrow task doesn't translate to human level performance in general. If you want to hear more about this, sorry, let me go to the sponsorship. I'm giving a TEDx talk on Saturday. You can go to TEDx, it's in McCaw Hall, or you can stream, they stream the whole thing live for free on TEDxSeattle.com or some such thing. So, back. You know how they have the commercials come back? All right, let me just give one more example that I think helps to understand why I think that we still have a very long way to go with machine learning. And that's ill-structured problems, right? And that's the difference between a board game situation. So take a sentence like people breathe air, okay? Let's say we want to represent what that means to a machine, whether we learn that or write down that representation. How do we represent that formally, right? We can't do that in logic because, right, you can't say for all x, person x implies breathe is air x, because there's lots of exceptions, right? What about somebody holding their breath? What about somebody dead? What about the temporal component, right? Sometimes I'm breathing, sometimes I'm not, et cetera, et cetera. It's quite complicated. How do we even validate if the representation is correct? So let's say I write down some logical representation. How do I check? In the case of a game, it's easy, right? I play it out, and I see who won. Well, who wins the representation of the sentence, people breathe air, right? That doesn't even make sense. What's the formal vocabulary that we're using, right? So if we want to represent this formally, we need to identify the vocabulary that we'll use to represent it to the machine. But we haven't defined a formal vocabulary that corresponds to natural language. My point is, I could go on, and I won't. My point is that so many problems are wide open, and they go way beyond the kind of pattern recognition from labeled data, whether it's supervised, semi-supervised, even unsupervised clustering that we see with something like AlphaGo. So our premise is that to achieve the kind of basic understanding you need for many of the challenges we have here, you need common sense knowledge and tractable reasoning. And how do we connect machine learning with that is one of the driving problems at AI2. So to summarize this part of the talk, to paraphrase Winston Churchill in his famous remarks about deep learning, he said, thank you. He said deep learning is not the end, it's not the beginning of the end, it's not even the end of the beginning. So if you're feeling a lot of that deep learning guilt, you still have time to catch up. Okay, second talk, AI2, founded by Paul Allen, and we're extremely appreciative, not just for the space and for his financial support, but also for intellectual leadership. A lot of the key projects come from Paul. He and I are in touch very frequently, and it's really been a privilege for me to work with him, and also to have his confidence to lead this institute. We're now 70 people. We're the largest nonprofit research institute in North America for AI. You have to put a bunch of qualifiers so I can say the largest, you know. But we are. So what's the research methodology that we use here? The work that we do is driven by grand challenge problems, and I'll describe those in a second. Relative to a university, we rely on team efforts. We try to make bigger long-term investments than the kind that they used to make at the University of Washington, you know, with a professor and a couple of grad students. And we try to set pretty ambitious goals, as you'll see in a second. At the same time, we need to have measurable milestones. So we're trying to avoid, right, this kind of pie in the sky, we'll solve AI, we'll solve cancer, just give us 20 years and good things will happen, right? So I like to think of AI2 as trying to bring together the best aspects of a startup, right? Being team-oriented, metric-driven, with clear goals, and the best aspects of a university, being informal, collegial, thinking about hard problems, and we have the privilege of not thinking about revenue. So what are our projects? We have a diverse portfolio of projects, and there are 4 of them. I'll talk about 3, and I'll let Ani talk about the work in the Plato project. Plato is our machine vision project. We have a phenomenal team there, led by Ali Farhadi, who's I think recovering from the CVPR deadline. And another project I won't have time to get to, but it's a phenomenal project, is Euclid, where we are using math story problems to study natural language processing. And if you're interested, go to euclid.allenai.org and you'll be able to see a demo. You give it SAT-style problems and it tries to answer them. And again, the key here is not the math. The key is that when you have a story or a set of sentences like the famous, what's the smallest number that's the sum of 2 cubes in 2 different ways? Anybody recognize that? Go ahead. That's right. So that was a story of Thomas Hardy went to Ramanujan and said to him, I was taken here by a cab with a completely uninteresting number. And right, and I'm sorry.
Is it 1729?
Well, don't ask me, you gotta ask Euclid. But yes, it is 1729, it's the smallest number. The point is that if you think about understanding a sentence like that, learning to understand a sentence like that, you see a couple of really interesting things. First of all, you really have to delve into a semantics of a sentence like that. You can't kind of send it to Google or use Word2Vec or some such thing. And secondly, if you think of the amount of training data, so let's say you want to learn a system to understand sentences like that, the amount of training data is very limited. You can't say, oh, sure, I'll just take 30 million labeled examples of mathematical story problems labeled with their answers, and I'll put it into an LSTM, you know, and I'll learn the patterns, right? There aren't 30 million SAT problems floating around. So you see some of the themes. We think about semantics. We think about situations where there's very limited data. When appropriate, we do leverage deep learning methods, but generally we're seeking to extend them, right? To go beyond the pattern recognition, to achieve knowledge, reasoning, natural language understanding, and more. I wanted to show you, to tell you about Semantic Scholar. Again, I could give a whole talk about that, but you know, they say a picture is worth 1,000 words. I like to say that a demo is worth 1,000 pictures. So again, this is available on the internet, semanticscholar.org. It's actually also available on your phone if you'd rather have your own demo. How many people have tried Semantic Scholar before? Wow, great. How many of you promise that you will try it by tomorrow? Thank you. And those of you who are not promising and didn't try it before, can we talk about this? Free pizza? Try Semantic Scholar. It's going to hurt you. All right, let me see if I can persuade you that the reason you want to do it is not to do me a favor, but actually because it's incredibly cool. So here's Semantic Scholar. I don't necessarily know how to maximize here. If I click on the green thing? Yep. Okay, yeah, I don't actually use this computer stuff. No, I don't use a Mac. Absolutely. So the idea is cut through the clutter. We've been talking about deep learning. Let me show you that example. If you type deep learning to Google Scholar, you get 3.8 million results, right? It's completely overwhelming. Each of those papers is cited by hundreds of other papers. Each of the papers that cite that are cited by hundreds of other papers. It's completely overwhelming, right? Information overload to the max. So what we've done with Semantic Scholar is we've put an array of features that allow you to drill down, to cut through the clutter, and home in on what you're looking for. First of all, when you're looking at the papers, we show you ones that are trending. They're mentioned here. This one was mentioned on Twitter recently. Maybe you're interested in that. We give you a bunch of metadata to home in on. So, okay, I want a Hinton paper. And the key phrase is mentioned. Oh, yeah, I want something. What did Hinton do on CNNs, actually? Let's look at that. Okay, and once, you know, with 2 clicks, I've gotten it down to 4 papers. And then I could dig in. We also automatically extract the figures and tables. That's Noah's work, I see in there. And so you can quickly at a glance see, oh, this is what the results look like. In this case, we just had 1. Let's see if we can do better than that with Deep Belief Network. Uh-oh, we're only getting 1. Usually you get lots more, and it's incredibly cool. Let's try one more. Oh, yeah, the famous ICML 12 paper, right. So again, here, and this works really nicely on the phone. You can quickly glance through, so I can kind of look and see, okay, they're working on this. Oh yeah, the ABN model does substantially better here, and you know, and I can share this on Twitter and so on and so on. So you get a sense of some of the unique capabilities of this. Also, again, you can tell at a glance, we're talking about aerial images. This is about CNNs using image patches, et cetera, et cetera. Another thing that we do is, okay, this is a 2012 paper, right, in deep learning years. That's ancient history. So I want to see more recent papers. So let me click on the citations to these papers, more recent ones. And again, all these are sorted by influence. So instead of having to look through all of them, there could be hundreds or even thousands, I'll get the more influential ones at the top. And we've built a model that categorizes, or I should say ranks, citations by influence. So if you look at this, let me just show you one more example, and then I'll tie it all together. So you know, another example, if I knew how to use a Mac, is we've also recently launched in Neuroscience. If you're interested in songbird basal ganglia, and frankly, who isn't interested in songbird basal ganglia? Then not only do we give you the metadata I showed you, but we also have some neuroscience-specific features. Like we'd say, okay, what cell type are we talking about? You know, axons or dendrites. What's the method that was used in the paper? Well, you know, we clearly want electron microscopy, and we want to go with, I can't even pronounce this. But again, we have a bunch of these neuroscience-specific features. Now, how do we do all this, narrowing down the neuroscience-specific features, ranking citations by influence? It's all data science models, right? We label some data, and we train models to tell you, okay, this is the brain region that this paper is about, this is the type of cell that's being used, et cetera, et cetera. It's machine learning all the way down, if you're familiar with that old joke. But data is very difficult to get here, right? Labeled data specifically. We have 10 million papers in our corpus, but labeling papers by the brain region, labeling citations, whether they're influential or not, all those are very hard things. And so we're not actually using deep nets for this because we don't have enough label data. And it's not exactly the kind of thing you can send to Amazon Mechanical Turk or even Spare 5, right, to label the data. Because you really need scientists doing this, or you need some tricks for distant supervision. Everybody familiar with distant supervision? No. So one of the things that we do, because labeling data by hand is very expensive for us, is we try to intersect the data with various databases or use various other tricks to automatically label the data. So distant supervision, broadly speaking, is an attempt to label data automatically using a reliable source. In the case, for example, of the brain regions and the various other specific terms, neuroscience-specific categories, what we did is we went to neuroscientists and tried to identify terms that were highly indicative of that particular model. And then we ran those terms, we matched them against papers, and we got a noisy labeling of papers that was indicative of, say, we're dealing with Broca's region in the brain, and then we labeled that way. So lots of tricks around labeling data. All right, I could spend the rest of this time doing this demo, but I will not. Instead, let me go back to the talk and watching the time here. Okay, so that's Semantic Scholar. We're planning to continue to increase its scope to cover the full biomedical literature in PubMed, and also to continue to get deeper into the semantics of the paper. So right now, we're categorizing them. We want to do automatic extraction of the key results of the paper. And again, everything in NLP these days is a flavor of machine learning, right? We can't write down patterns to do the extraction automatically because they're too brittle. So we need to learn the patterns automatically. Let me talk about the Arista Project. The challenge in the Arista Project is question understanding. Let me actually skip forward quickly here's some examples. These are some of the questions that we have. Fourth graders are planning a roller skate race. Which surface would be best for the race? A, B, C, or D? And you can see these types of questions. Some of them are actually longer. They involve maybe some diagrams, thinking about life cycles. If you look at these questions, you'll see some interesting things. Number one, they're on a wide range of topics. Number two, the language that's used is pretty varied. And number three, you need common sense background knowledge to answer these things. It's not the case that you can just do this based on the textbook, because the type of questions that they ask, and these are questions from science tests, they expect the kids to be able to take the principles that they learn from the textbook and apply them to real world situation. Now, who cares? Who cares what they do in these tests? Who cares whether we can answer these questions or not? And the answer is very simple. Paul Allen does. No. But why does he care? And the answer is that this is a benchmark, right? This is a test for understanding natural language processing, for learning common sense knowledge. Okay, we can't just go to the Google Knowledge Graph or Satori or Freebase and just get the answers from some database and look this up. We have to understand, right, what are the properties of sand versus gravel? What surface is most appropriate for roller skate races, right? We have to think about these things in terms of friction. And so there is no database that has this information. This information is either in textual form, or it's in images perhaps, in diagrams, or maybe it's in videos. We have to figure out how to learn this from the real world and automatically generate the knowledge bases required to answer these types of questions. We also have to learn how to understand the question in the first place. And that's quite difficult because the questions vary in topic and form, and we test ourselves on unseen questions, right? Standard machine learning methodology. We train on as many questions as we can find, and at this point we have several thousands, but then we have to test on unseen questions. Very, very hard problems. And if you're not convinced that these are hard, let's look at some of the diagram questions in Arista. By the way, I'm not making this up, right? Our kids can do this. Of course, our computers can't. So here's a thermostat question, right? You have to be able to automatically make sense of this representation. We have tabular questions where there's dates and sunrise and sunset time. You have to make sense of that. We have these really strange things, right, where you can't even decide, okay, what's really happening here if you're a machine. There are no machines today that can solve these range of problems. Your own work notwithstanding. We actually ran a Kaggle competition. Several thousand teams entered. Nobody was able to get above 60% on what we call NDMC, on non-diagram multiple choice questions, let alone the ones with the diagrams, let alone the ones that aren't multiple choice. So these are very, very hard problems. And if you look at the problems that other people in the community are working on, for example, the famous baby data set, they're really substantially easier problems. That's fine. There's room for all kinds of things. You have to walk before you can run. But these really are some of the toughest problems in all of natural language processing. And the goal of the Arista project is to work over time to solve these. We have specific metric goals, and we're very proud that we've been consistently increasing our scores on this test and continuing to do so. At this point, I'll stop. I'll remind you that we're hiring. I'll remind you that if you go to the top, particularly on a nice summer weekend, this is what the view looks like. So there's fringe benefits to working at AI2. And I'll turn it over to Ani to talk about Lida and his work. Thank you.
Hi, my name is Ani. I am a research scientist in the Plato team, which is the computer vision team at AI2. And today I'm going to talk about a couple of our projects over the last few months. And this work has been done in collaboration with Min, Eric, Mike, Hannah, and Ali, some of whom work at AI2 and some of whom work at UW. So today I'm going to talk about, in particular, the usage of attention models in neural networks. And I can summarize attention models, I can simplify and summarize this in two sentences. If you have two sources of information, and let's say that they're two bags of information, and you want to combine these in a way that you want to take one bag and say, what's the most relevant piece of information in the other bag with respect to one bag? Then this today, we globally refer to as attention, because you're taking one bag and you're attending to different pieces of information in the other bag. So imagine if you had a question answering system about images. I show you an image and you say, how many horses are there in this image? So here you can think of the image broken down into different image patches. So now you take the question and then you start going through each image patch. So you're starting to attend to each image patch. Another example is where you have a machine comprehension task where you have a paragraph and then you have a question about the paragraph. In this case, your context bag is now the different words. You take your question and you start attending to these. And so this is the general framework which this is the general framework which is used in some of our problems. And so I thought I'd give you a flavor of what we're doing. I'm going to start talking about question answering in the vision domain. This was work that we did in the early part of this year. And I'm going to end with some work that we've done in the language domain. And these results are very new. We've just got them about 10 days ago, so I'm excited to share them with you. Okay, so let's start with diagrams. So why are we interested in diagrams when most of the computer vision community is focused on natural images? Everyone's working on the latest object detection, object classification, tracking in natural images and videos. But here at AI2, we find diagrams very, very interesting. First of all, diagrams often represent complex phenomena that natural images might find it hard to represent in a single natural image. For example, you can look at this food web, which talks about who eats whom in an ecosystem. And you'd be hard-pressed finding a single image that tells you about this. Because diagrams represent complex phenomena, they are really good test beds at building and evaluating reasoning frameworks. And of course, they're there in our 4th and 8th grade Arista exams. which makes it very challenging and a fun problem to work on. So where do we start? There's a lot of variation in these diagrams. And given a diagram, you want to answer some questions. So the first thing that you want to do is to be able to represent this diagram. Of course, you don't want to build one representation for food chains and then go back and say, well, now I have phases of the moon or solar system, so I'm going to build another representation. So you want to find a common representation which will span at least a large variety of classes. And the representation that we've been using, that we've come up with, is called a diagram parse graph. So what is this parse graph and how did we come up with it? Well, we spent a fair amount of time trying to see if other people had worked on this problem. And it turned out that in the graphics community, there's been a lot of work on how do you represent a diagram, what makes a good diagram, what information is easily parsed by humans looking at diagrams and visual illustrations. And in particular, I like this work, which was done about, say, 12 to 15 years ago, called the language of graphics. And they propose a framework for analyzing the syntax as well as the meaning of a large class of diagrams. So here's a very simplified view of his entire thesis. He says, a diagram is a composite graphic which has three parts. You can think of a graphic space, which is like the canvas on which the diagram is built. Sometimes this space is just white space, but sometimes it has meaning. So up and down have meaning, and distances have meaning. On this space lie a set of constituents, which are your actors in your diagrams. And then these constituents are related with each other and with the graphic space through a bunch of relationships. And so you can extend this very simple concept to represent a very wide variety of diagrams. So here's an example. So now we have a foodware, and of course this is one of the easier diagrams in our work, but it serves as a good illustration. And so now you can break this down into saying, well, there's some constituents, which are the actors, in this case animals, and these constituents might be visual, but they might also be textual. And they might also be composed of diagrammatic elements like arrows. And so each is a node in our diagram parse graph. And now different combinations of these constituents are related to each other. And they're related to each other via a set of predefined relationships. So for example, horn sharks is a textual element, and this drawing is an illustration of horn sharks. And these are related through what we call a labeling relationship. Whereas these two animals are related through a linkage relationship. And so you can kind of get a flavor for how you can start from the low level. You can start saying, who are the actors, how are they related, and build up this diagram parse graph. So how do we go about doing this? So our approach is a hierarchical approach. So we start from the very bottom, and we use object detectors to detect the different constituents. So we have detectors for, what we call blobs. In that image, it was just the animals. We have detectors for diagrammatic elements like arrows. You can think of OCR as one of our detectors to detect textual elements. And then we build on top of that to combine these to form relationships. And the heavy lifting is done by the high-level component, which puts all of these guys together to form diagram parse graph. So let me quickly give you some examples. So detecting constituents. Well, there's been a lot of work done in computer vision to say, well, how do you detect humans? How do you detect dogs in an image? But we found that off-the-shelf techniques don't really work really well for diagrams. And there's a bunch of reasons why. But off-the-shelf frameworks work really well. And the general framework for object detection is you generate a bunch of candidates, and then you score them through a machine learning model. And of course, over the last few years, machine learning models that have been very successful in object detection are deep neural networks. So here's an example for arrows. Arrows look really easy, but they're actually very, very challenging. Why? Because basically an arrow is just a line. And there's a lot of diagrams where the arrows don't have arrowheads. So now you're just saying, out of all the 2,000 lines in this image, tell me the ones which are actually arrows. So how do we start? Well, we have image processing techniques to find all sorts of things that look like straight lines and curves. So you have your standard half transforms, boundary detection, canny edges, and so on. And so we get somewhere between 2,000 and 5,000 candidates. And now we score these candidates using a neural network. So if I got this as a candidate, the orange line, and I had to give this image patch to a neural network, it would then be able to tell me, well, I think this looks like an arrow because there's something at the end and there's something at the beginning and so on. But of course, if I just gave this image patch to the network, it wouldn't know, well, are you asking me to score the orange line or are you asking me to score the black line? And so the way we get over this task is to say, instead of giving a 3-channel image, which is RGB, we give a 4-channel image, where the first 3 channels tell you the image components, and the 4th channel, we actually put a Gaussian around the candidate that we have detected. So we're sort of telling the neural network, well, tell me if this guy is an arrow. And then we give it to standard computer vision trained deep neural nets, and they do a pretty good job at this task. So we extend this framework to all the different constituents that we have in our dictionary. So now we have a bunch of constituents, and so we want to start building up relationships. So we have a predefined list of relationships that we're considering, which is a subset of what all diagrams have, but this works well for our task right now. And the way we do it is we say, well, if I take a visual illustration and a text block, does the text block talk about the visual illustration? So how do I do this? Well, I can write down a bunch of features about the spatial layout in the diagram, the orientation, as well as I can provide information from the low level, which is what the deep models are giving us. And then I can take an off-the-shelf machine learning model, such as random forests, and train it on this. And then it will score tuples of constituents as I think these are in this sort of relationship, and I think these are not. On the other hand, there are some relationships which are just between the constituents and the background space. So for example, is this text box an object, or is this the title of the image? And so we have various techniques that can help us score these sorts of relationships as well. So now, the thing to keep in mind is, we're having these low-level and mid-level detectors give us candidates to the higher level. Now the higher level module is not able to hallucinate a new constituent or a new relationship. And so it's very critical that the lower level modules are tuned to high recall. What that means is that if there's something in the image which you think is an object or is a relationship, give it to the high level. The high level guy can then prune out bad detections using not just local cues, but also global context. So how do we do that? Well, one way to think about this task is to say, if you gave me a bag of detections, how am I going to start assembling my diagram parse graph? Well, you could think of it as, well, I'm going to take the one with the highest confidence and put it in. And then I'm going to take the guy with the second highest confidence and put it in. But only if it makes sense given the first guy. So if I have a relationship in this part of the image and I have another detection which is very close by, but typically diagrams aren't drawn this way. They're drawn so that things are far away and neatly placed and perhaps symmetric. So then you can think of building a diagram parse graph as a sequential growing of your diagram, of your parse graph. So the way we do it is LSTMs have been used very successfully for sequential problems. So we start feeding into the LSTMs feature vectors that describe all the candidates that the low level brings up. And the LSTM starts outputting a yes or a no. So we feed in one relationship, it says, yep, I think this is a good guy. We feed in the second relationship, and it may or may not add it in, given contextual cues. And so it slowly starts building up your diagram parse graph. So how well do we do? Here are some qualitative results first. So the first row are the original images. The second row are the, I'm showing you the constituents that the LSTM has picked out. And the third row shows the relationships that it has marked it. So you can see it does I would say, a fairly decent job. It's not exceptional, but it's much better than random, of course. here you can see a food chain, and it starts marking out all the blobs. It starts marking out the textual elements that correspond to the blobs and how they are related with arrows. Here you can see this is a circular relationship where it shows you the different phases of the moon as it goes around the Earth. It detects that correctly. This is a diagram which just has one object, but it has parts of. And so it has now figured out that there's only one center point in the graph, and everything else is like a sort of like a star-shaped network. And here it's figured out that no, there's multiple objects in the scene, and each of them is just labeled with a single text box. And so we have a metric to see how good this model does on our data set, and it's called the Jacquard Index for Graphs. So basically you look at all the constituents and relationships which are labeled in graph truth, and you look at your detections, and you have some score of overlap. And so these numbers are not super important for this talk, but what it tells you is that we're at about the 50% level, which means on average, we can get about 50% of all constituents and relationships in these diagrams. So there's a lot of work to be done, and this is the work that we're continuing to build upon. So now we have, given a diagram, we have a parse graph for the diagram. But the real goal is to be able to answer a question. So how do people in the visual question answering community do this? This diagram has been taken from a paper from Virginia Tech. So the way they do it is they say, well, here's an image. I'm going to pass it through a convolutional neural network, which are great at detecting and classifying objects. And here's a question. I'm going to pass it through an LSTM, which are great at embedding sentences. And then I'm going to combine these at the end and give it to a neural network. And this guy is going to tell me the answer. So this is, as Oren said, neural network land, age-old research. And now people have extended upon this idea. So instead of giving the entire image, they give different patches of the image. So as I said before, the question can then start attending on each patch, presumably to come up with the thing saying, I see a horse in this patch, I see a horse in this patch, and hence the answer should be 2. So how do we use this in our framework? Well, what we do in our framework is we say, given an image, I just told you how we get to a diagram parse graph. And diagram parse graph is composed of different relationships. So we convert each relationship into a natural language sentence. So for example, if there's deer, there's an arrow, and there's grass, we say deer is connected to grass. But keep in mind that we're only writing down the syntax of this diagram. We're just saying deer is connected to graph. We have no idea about the semantics. So we have no way of knowing that this means that deer eats graph. That's the work of the neural network to figure out, given training pairs. So you're now embedding each relationship in natural language form, and then you give it to an LSTM to get some embedding. You take your question. In our particular case, we had multiple choice with 4 choices. So you take your question with each choice and embed it, and then you give it to what I spoke about is your attention model, which is basically taking the question, taking all the different relations, and trying to see which relation makes the most sense to answer this question. So to trivialize it and give you a very simple example, if there were 2 or 3 relationships from the diagram which said deer is connected to grass and lion is connected to, I don't know, a bison, and the question was who eats grass, the model is trying to figure out that I think eats is connected because I see this over and over again. So I'm going to look for the relationship which has grass, and I'm going to pick out the noun on the other side, which is deer. So this is what the model is supposed to do. And how does it do? Well, so first let's start with the qualitative results. I would say that the model does decently well. It's good at picking out single first order relationships. What it's not very good at is doing higher order relationships. So if there's a question that requires you to parse the graph in complicated ways and do any sort of reasoning on it, attention models haven't got to that stage yet. It's really good at saying, well, I see something about grass, I'm going to pick out the guy who talks about grass, do a little bit of reasoning to say, well, am I expecting to find the word before grass or after grass, and then pick out the word and give it the answer. So for example, here it says what comes before second feed in this diagram. And so you can see that it's attending to this relationship here. It's saying second feed. I'm going to find the relationship to second feed. This is something called OV position, and then I'm going to give you this answer. Okay, so that was some work that we did in the visual domain. I'm going to move on to the second piece of work, which is in the language domain. So, as Oren mentioned, a lot of question answering tasks require unbounded knowledge. It's not clear how to get this knowledge, and these are, open problems that we're working on in AI2. When you have a question, first of all, you need to find knowledge on the web or through books or through textbooks. But there's also a lot of common sense knowledge, which we don't really know how to gather at this stage. And so a compact version of question answering, one of the compact versions is machine comprehension. In machine comprehension, you're given a question, but now you're also provided with a paragraph. And you're told that the answer lies in the paragraph. So in a sense, you're trying to say, well, I'm going to bound the knowledge. And now we can research how do we extract knowledge from a specific set of information. And so we find this problem interesting as well, because now we can say, well, we can sort of slice down the problem and say, if we have the knowledge in a paragraph, do we have natural language processing systems that can pick out the right answer? And this has been a problem which has had a lot of research. But recently, I would say about 6 months ago, folks at Stanford released this thing called SQuAD, which was the Stanford question answering dataset. And this is the largest machine comprehension dataset with human-written questions and answers. So they've taken a bunch of paragraphs from Wikipedia and crowdsourced these paragraphs out and asked mechanical Turkers to write down questions about these paragraphs. And now the answers to these questions are not multiple choice. So random is not 25%. But the task is to tell you the start and end position of the phrase wherein the answer lies. And so you can see now that even though the knowledge is confined, the task has been made a little harder. And this is actually a fun problem to work on. And so we said, yeah, let's try to see what we can do on this problem. So diving straight into it, here is the model that we came up with. And I'm going to take you step by step through the model, and you'll see that actually it's a very simple model. It's you can break it down quite easily. So the model is hierarchical in nature. It has a bunch of layers that start at the character level and go all the way to the question answering level. So how do we start? Well, let's start right at the bottom. So the first layer is character embedding layer. So just like in the image space, you can take pixels and pass them through a convolutional neural network. Here you can take characters and pass them through a convolutional neural network. At the same time, you can also do embedding at the word level. And so here, instead of doing everything from the character level, we can also leverage work that other folks in the NLP domain, the natural language processing domain, have done in embedding words. And so we use these things called glove vectors. And glove vectors have been trained on other corpuses. And glove vectors basically embed words which have similar meanings with similar vectors, and words which have meanings which are not similar with vectors which look very different in their space. So we start at the character level as well as the word level. And of course you might ask, well, if you're already embedding at the word level, why do you need character level? Well, that's because word embeddings are very good for common words like book and table and screen. But if you had to find the embedding for my name, you would not find it in their corpus. And so for proper nouns and what we call outer vocabulary words, you need a specific kind of embedding, which is character embedding. So now you've embedded individual tokens. Now we go to the next level, which is saying, well, but a sentence is not a bag of tokens. It has some meaning and some order. So how do you embed these tokens given knowledge of the previous and the next words? And this is done using LSTMs. And after a couple of slides, I'm going to show you how the vector spaces change from layer to layer. And it's quite interesting to see, once you start putting the context of previous and next words, the vector spaces get a lot more interesting. So at this stage, what you've done is you've taken your context, which is just a another word for paragraph, and you've embedded in. You've taken your query or question and you've embedded in, and now you want to combine them. And this is where attention comes in. So in the past, people have worked on taking the query and then trying to find the word in the paragraph which is most relevant to answering the question. And this is called attention. And they've also had more fancy extensions that, well, the attention at a particular time step should be dependent on the attention on the previous time step. Well, our research here has shown us that we can actually simplify attention, bring it down from the higher layers, and just use attention. You can sort of think of attention as a feature. So instead of attention doing all the heavy lifting, you do attention both ways, from query to context, context to query, but now pass in the vectors into your modeling level. So attention can just be thought of as yet another pre-processing layer to capture more rich information between the query and context. So now I can now think of my model as character embedding, word embedding, phrase embedding, and then query-aware embedding. So you're slowly building up more and more information. So what do these two attention matrices tell you? Well, context to query is trying to capture which word in the question is most relevant to my current word in the paragraph. And the other one is trying to do the opposite. So then we give it to a modeling layer, which is LSTMs, and then we give it to an output layer, which helps you answer the question. So if your thing was multiple choice, you would you'd have 4 options. We have a particular thing where we have to tell you the start and the end location. And so this output layer can be swapped in and out based on your task. So now let's look at some visualizations. Well, so you might recall that we have a word layer and then we have a phrase layer. So I took all the feature vectors that we had in these two spaces, and then I reduced the dimensionality to 2 using a very common technique called TSLE. And then I looked at specific clusters of words. So I said, okay, let me look at all the months. And you can see that all the months are nicely clustered here, except the month of May. And why is that? Well, if you think about it, it's because May can be used in 2 different ways. It's either a month, or it's just another word which has some meaning. But now if you go to the phrase embedding space, phrase embedding, you might recall, says, I'm also going to use the previous and the next words. And now when you look at it, usages of the word May, when it's used as a date or a month, are now clustered much closer to other usages of months. Whereas usages of May, when you have, these may be, effect, and may result in, the state may not aid, are now clustered further away. So you can start seeing what your model is doing. It's using the context of previous and next words to change your vector spaces a little bit. Here's another interesting thing. So, yeah, that'll be done fine. So this is a table that's hard to parse, and let's go through some of these examples. So now we have query words, and we have words from the paragraph. And I wanted to see what word in the query looks like what word in the paragraph. Because the network is structured such that you want to start relating words from the query to words from the paragraph. So, and I said, well, let me look at it at the first layer, when no work has been done. So the first layer, if I look at the word when, well, it looks like just another bunch of words in English. But if I start going up at the phrase level, which has context of nearby words, if I look at when, it starts picking out dates. So now the network has associated the word when in the query with the answer most likely being a number. If you go to where, it starts picking out cities. It also starts picking out words that reference locations, like location, outside, nearby. Who starts picking out names. City starts picking out cities, and so on and so forth. So you can see that it's starting to associate questions and contexts. And now let's go to the top layer, which says attention. So let's look at this example. This is a nice example here. So this is a paragraph about natural reserves in Warsaw. And the question is, how many natural reserves are there in Warsaw? Now, this matrix each row is a query word, and each column here is a word from this paragraph. So the number of words here is equal to the number of columns. And now let's see what it does. And the words here are just, I said I'm going to put a threshold. If it lies above the threshold, I'm just going to write down the words here just so that you guys can look at it. So if you look at natural, it just matches natural. Reserves matches reserves. But many starts matching words that look like numbers. And so it says, well, many could be hundreds, or few, or among, or 15, or 30. And so now you can see here that it's matched the remaining words in the question with these guys who basically are the same words. And now it can localize, this is conjecture of course, it can localize this to be the answer. So this is totally conjecture, but it's a nice visual representation of what I think the network is doing. Okay, so using this network, how did we do? So the Stanford QA dataset is very comprehensive. They give you a validation set, but they don't provide the test set. You have to upload your code and evaluate it online. And there's been a flurry of experiments that other research teams have been doing. And as of this morning, we're at number 2. What's interesting is that the guys who have now jumped up ahead of us are also using co-attention. So indicating that they're also found very similar findings to our research. And I'm going to guess, I haven't read that paper yet, but I'm going to guess that co-attention is just a synonym for our bidirectional attention. So it's interesting that they've also found similar things in their research. And this is just ablation studies to show you, well, I have so many things in my model. If I remove this guy, do I get worse? Yes. In most cases, if you remove different parts of a model, our performance gets worse. This is my last slide. We did a comparison to a more traditional NLP model. So this was a model that was suggested as a baseline by the Stanford folks. And they said, well, instead of giving deep learning, what we're going to do is we're going to take features that the NLP community has traditionally used and give it to a logistic regression model, and then give you a baseline which you can now compare your models to. And what I was interested in seeing was, well, deep neural networks, and we found that they work better than these traditional NLP features, but are they very different? So are we now answering questions that the NLP guys could not, and vice versa? But it turned out that, in fact, the questions that were unanswered by the deep neural network were also mostly unanswered by the baseline. And once again, this is conjecture, but I'm going to guess that if you looked at the guys who are number 1, I'm going to say that this 509 is going to go even lower. So it seems that deep neural networks are very good at picking out these simple syntactic meanings and help you answer questions. Of course, I must add that the Stanford QA dataset does not have a lot of reasoning. A lot of the questions are from either 1 or 2 sentences, but on this specific task, these models are doing pretty well. And that's all I have. Thank you.
So just to make this fun, if you guys, please stand. If you have any questions on bidirectional attention mechanisms, you can ask me. Any questions about the first? I think we have time for a few questions if anybody has a burning question.
The question on the bidirectional, very interesting. Just curious, have you tried building ensemble models with the traditional and the NLP techniques and comparing the confidence?
So when it comes to ensembles almost always help. So when we said that we were number 2 on the list, if you look at the top 5, they're all ensemble models. And the next 5 are the single versions of those ensembles. But the ensembles that we have built are ensembles of our own model. We were interested in building an ensemble with the NLP model, which is why we did the analysis. But initial indications are that ensembles will help, but not as much as we hope.
When you're building the diagram parse graph and you're adding in objects one at a time, do you do backtracking? Like if you start trying to add something and all of a sudden the confidence dies, you backtrack?
So in the current model, we don't. What we could do is the LSTM goes sequentially, we could have another LSTM goes the other way. And so we can have one guy basically, with no backtracking from left to right, and the other guy with no backtracking from right to left. So this is sort of cheating backtracking. But we could have more traditional versions of backtracking, and I'm sure we'll have.
Watch things in parallel. Right, watch things in parallel with different criteria.
Perhaps, yes.
So have you tried bidirectional LSTMs instead of LSTMs?
So in the bidirectional attention flow models, the LSTMs were all bidirectional.
Okay.
In the initial work, they were not, but now we are convinced that bidirectional LSTMs can give you a bit of a boost.
Yeah.
For the previous project about the presentation learning on just curious about how you get your label data.
It was a lot of effort. We had to take about 5,000 diagrams and pass them through Mechanical Turk. But these are not easy tasks, like, is there a human, is there a car? And so me and my colleagues had to break down this task into, I would say, 12 to 15 Mechanical Turk tasks. It took us 3 months to label just 5,000 images. It's been, it's very difficult, and it's not easily scalable, but even 5,000 images can get us somewhere.
For some of the things like the arrows, which should be like easier than the constituent.
So an individual task like, tell me where the arrows are, this is easy for a Turker. But the minute you start going into label the semantics of an image, things start getting ambiguous. And in Turk, you only have about a little bit of real estate space and a small attention time span for the Turker. So you have to explain your task where it takes less than 30 seconds for them to read. And that's very hard.
And just a follow-up question for things like arrows, did you use a model, like pre-trained model and build on top of it?
Yes, we found that pre-trained models almost always help in this work.
Just wondering, what's your experience using Mechanical Turk? I mean, do you have any way of validating the results you get through that method? Or
So the way we do it, and I'm sure most research places do it, is you get one bunch of Turkers to get your results and another bunch of Turkers to validate them for you. That's typically how it's done. Of course, it adds another cycle to your loop,
yeah,
and it takes more effort.
right.
Actually, there's some interesting new results, particularly out of Dan Weld and his group at UW, that showed that often you can get away without that, where you can pre-qualify folks so they're not cheating, and then just rely on one, and you get some noise in your labeling, but it's a lot more efficient, right? Because that's right, it's costing you double, right, to have that level of validation. So there are some interesting ways to make that more efficient. So happy to take more questions informally. Thank you so much for your attention, and I do have to remind you that for building reasons, we do need everybody out by 8 o'clock. But we still have a little bit of time until then, and Maria is still there if you want a job. Thank you so much.